researcher at the UMR eSpace Development. She received her PhD in Applied Mathematics and her habilitation on Systems Theory from the University of Perpignan. Her research focused on the study of distributed parameters systems and related control theory by means of cellular automata models. She has developed new tools for studying some analysis problems, such as identification, spreadability, regional controllability, and observability. And her talk is 40 minutes, and I will let you know when you have 10 minutes left. Can you
hear me?
Yes, we can hear you.
Everybody, okay. Thank you very much. Thank you very much to the organizers for this very special session of the edition for the Automata conference. It's a bit special for all of us. Then I will try to do my best, because I'm in a region. I'm a bit far from all the high technology, but I will try to do my best and to make my talk. Let me and I would like to thank the organizers for inviting me to give this plenary talk. Let me see when I can share my screen. Normally it okay. Normally it works. Sorry. Do you see my screen?
Yes, we'll see it.
Okay, I will shut the camera, because my connection is a little bit not very high. Then I will shut the camera in order to have only the screen and my voice. Sorry, where can I do it?
Oh, I can stop it for you.
Yeah, please. Okay, very much. Okay, this work was carried out with some of my PhD students, Ardridi and Theo Pleni, and in strong collaboration with Franco Bagnoli and some colleagues from France, Laurent Lefebvre and Clément Rajewski. We are all working on some control and observation issue by means of cellular automata. As you mentioned, I am a full professor in computer science at the University of Perpignan, and I have a background in applied mathematics and control theory, and my research is focused on how to extend some concepts of systems theory using cellular automata. And this project is going from started a few years ago, and with the aim of using cellular automata models as alternative to partial differential equations for many applications, because all my work is, of course, theoretic, but it's really motivated by, strongly motivated by many applications, especially environmental applications. The outline for my talk, I will introduce first distributed parameter systems, how to describe system related to inputs and outputs, and some concepts related to system theory, controllability, and observability. After I will This is something which is done some years ago, how to introduce control and observation in cellular automata models, and then give cellular automata as an alternative to partial differential equations and to distributed parameter systems. Then I will see something about regional controllability of cellular automata by the main results given by Kalman condition, but we have from some years ago we have worked on some alternative methods to Kalman condition because this condition is it works only for linear systems, and we want to investigate other methods and to generalize this method to generalize how to prove controllability and observability by means of cellular automata. Then the first thing, when we deal with the systems, we can before we can describe systems just as a black box. With the inputs and outputs, and we just know what the input we put, what with the input we act on the system, and how it's the response of the system. And according to the relation between the input and output, which are connected by a convolution equation relation, we can use the transfer function to represent the input-output relationship, and through the Laplace transform. But this is a black box, and we can do nothing with the system. And if we want to really analyze the system in internal state of the system, we should go further and go to what we call the internal description with the state equation. And this is it has been done through this state variable, and this state variable we have the input which gives the internal state of the system, and after we have the response and the output. And we have some functions f and h which are according to t, z, and u, and according all the variables. When all the system's components, when we have state, inputs, outputs, and all the coefficients, when they are dependent on space and time, such systems are called distributed parameter systems, and they are in the past usually described by partial differential equations, integral differential equations, some delayed equations, etc. But everybody knows how it is difficult to deal with these partial differential equations from a theoretical point of view, the analysis, and also from computational point of view. And that's why, especially when we are dealing with the practical applications, and that's why we turn to some alternatives for modeling this kind of systems, and we go to cellular automata. The concept of systems then has been extended to include not only technological or physical system, because it was the first meaning and objectives of system theory and of the control theory. It's for technological issues, but now we are dealing with biological systems, with ecological systems, many economics, and many environmental systems. We want to extend all these theories for the applications, for practical applications, and that complicate and complexify the system and the study. Then when we have two things which are very important in DPS is input and outputs, which they have a reality in the system. They can have controls and measurement on the system, and these controls can be they are specially extended. then they have reality, and they can be pointwise actuators. They can be zone actuators, and they have many types. And depending on this structure, the solution of the system of the equation, the state of the system may have different forms. And the concept of control has been defined as the method how to control a system through the application of inputs. It's not only we act on the system and we let him go where he wants. No, we want to act on the system in order to achieve the system, in order to steer the system to some predefined objectives, and that is something which is not obvious. As I told, DPS are usually defined by three operators. They are the dynamics operator, which gives how the inputs are applied on the system, and an output equation, which gives the measures how we are observing the system. And through this operator, and depending on the types of the operators, if they are linear, if they are bound, if there are many properties of these operators, we can have, it depends on the solution of this equation, depends on the nature of these operators. And we have two key concepts which help to understand the functioning of the system. And this is the concept in the analysis of such systems. They are observability, controllability, and observability. And these two concepts will be studied through this operator B and C. And this is very, very important, these two operators. The controllability, then it's just to recall, it concerns the ability to steer system from any initial state to any desired state. Of course, these states should be in some suitable spaces. Of course, for continuous system, for DPs, we are dealing with Hilbert spaces and etc. But for cellular automata, things are very, very different. And many types of controllability. We have global controllability, we have exact controllability, we have weak controllability, when we can achieve only state which is near in some region near the desired state. And we can also have we can be interested in only in achieving some objectives on some region, some area. We are not interested in the whole system, and sometimes it's very complicated to achieve the objectives on the whole system, but only on some area. And this area, practically, it means some area which are vulnerable, which want to protect, etc., etc. And the effort is not the same when we want to act to achieve objectives on the whole. It's not the same as when we want to have only for a small region. And the observability, this is a dual concept of controllability, and we have a state and we want to go backward to the initial state, and how to reconstruct the initial state. What we mean with initial state is not only the state at t equal to 0, but at t equal t0, this is some time from where we want to study the causality between some perturbation of the systems and what we are observing now. then it's very important this concept to even in some applications now in biodiversity, when we are observing the loss of biodiversity, but we don't know when and where this the cause of this loss happened, and if we are able to reconstruct in the past, some states in the past, from only partial observations on the systems, this is very interesting to understand the evolution and even to predict what will happen after. Then in this section, I will just recall what it is done from some years ago, because when we wanted in this big project, we wanted to use Cellular Automata for our purpose in systems theory. The first thing is to define and to formalize Cellular Automata as DPAs, as with external inputs and with measures, and all this work it's around this section. Then we have, of course, the classical definition of Cellular Automata, and with the neighborhood, we define the neighborhood according to some norm, classical norm, and we define the transition function in this way, and we define for the lattice for when we deal with the infinite lattices with the dimension d, we can introduce this very famous metric, and with this metric we have a structure of compact space, and we can have with the induced discrete topology, we can have the continuity of the function, the global function f, and this will give us the possibility to give a Cellular Automata as it was given even before as a dynamical system. The configuration or state of the system at t+1 is fs at the image of the state at time t according to the global function f, and with some initial condition s0. Now we want to add some controls, some actions on the system, and not only on everywhere, not the distributed action, but only on some cells. For some cells, we will act on these cells, and we want to have how the system will behave with this action. Then we define everything according to what we know for DPAs. And just to go further, now we can define G, global function, global control function, which at every action U, we have a new state in this state space. And we define some regular spaces in order to have what we call here the global dynamic F, which depend on the state at time t-1 and on the control at time t-1. At each time we have an action, and all this sequence of actions will influence the state of the new state of at the next time. And this operator also have some properties like the global function f. in the same sense, we are not, we don't know exactly ST. We don't know the state of the system, but we know only, we have only an observation of partial knowledge of the system. And this is through an operator, H, which is the observation operator. And these two will play the same role than B and C in the operators B and C in the DPS. Then the obtained CA statement will be very close to the usual discrete time distributed parameter systems augmented with the output function. This is the output function. And all the concepts will be studied according to these two operators, not in what we when we are acting on a system, there are many possibilities to act on the system. Here, for example, we have a region, we are only interested, we have one Cellular Automata, we are interested only in achieving some objectives on this region, the controlled region, and we want to act on these two cells, but at each time. Then we have to act on these two sets. But we can act also on the boundary sets, and we will talk about the boundary controls. Then even we just act on the boundaries of the lattice, and we can have some just like for us for Cellular Automata, we can fix boundary conditions, and these boundary conditions may be unknowns, and we will try to find how to act on the boundary, how to fix this boundary condition to have some behavior of the system. And to CA, of course, we can have this area and this boundary cells which surround the controlled area, the controlled region. Of course, for controllability and for regional controllability, we have to fix something. We have a small region in L. We have this new space, which is only configuration restricted to the small region, and we have the system is said to be regionally controllable or controllable if it's only if omega is the system L, the space L, and we have to the state, the final state at time t will be the desired state, what we want to have and to achieve on this area. Sorry, I will. This is what I explained for the boundary, because this is what we are studying for many work, and we have some results regarding this part. This study was focused on Boolean CA, and we will apply certain sequence on boundaries until the desired configuration appears in the target region. And the target region will be as it's mentioned here, but we can have many here, many cells. The observability and controllability, they are conceived by Kalman in the 1960, and there is a very famous theorem of Kalman, which gives the condition of the controllability of observability, or observability is the same. We will have, because there are dual concepts, dual notions, then we have this controllability matrix, because first Kalman dealt with linear systems and with the finite dimensional systems. Then when we have only a set of partial differential equations, and we have a set of differential equations, and we are in dimension n. And then we built this controllability matrix, and if the rank of this controllability matrix coincide with the dimension of the system, then the system will be controllable. We will see that this condition for observability is the same. And we wanted to first, the objective of all this study, first to say that this Kalman condition will work also for cellular automata, and we want to go behind and to go further and to try to find other approaches for proving the controllability of systems of cellular automata. We are dealing with Boolean CA, then we can consider the Jacobian of the Jacobian matrix, which is defined related to the Boolean derivative, and this is a work which is developed with Franco Bagnoli, who works a lot on Boolean derivative, and we can have this formulation of the Boolean controlled CA. The configuration at time t+1 is GS configuration at time t, and plus B with the control vector the control vector U at time t. And we have this matrix related to restricted to omega. It represents the control operator, and UT is the control vector. And we have some characterization results, the same characterization results, but with G, the Jacobian matrix, who will play the same role as the dynamic A for the DPS. But what we have obtained here is the rank of this matrix must be equal to T, and here we can define the horizon, the time horizon for which we can achieve the controllability. Then the controllability depends on the dimension of the number of the size of the CA, and it depends on the time horizon. And we can have for T, for some T, we can have the controllability, but for others, no. Then we have this result. I won't give the proof. I just wanted to give you some results and show you how we have applied this result. There is, of course, people who deal, when I discuss with people who works on cellular automata, it's very difficult to develop algorithm and to decide even for the decidability of to decide if some generic rule is controllable or not. But we can decide, and we already obtain some results and some classification, at least for elementary CA, and we find some classification for which rules are it's decidable. For some rules they are controllable, and for some others no. And depending also on how, as what we say, it depends on the size of cellular automata of the lattice. Then for linear rules, or what we mean peripherally linear, that we have linearity only for left side or right side. And this can be done iteratively. Then the least external site can control a site in the target region. No, which flips the value if wrong. And then this can be repeated for all sites to be controlled, and we obtain an algorithm to find this and to go to the final T and to go to the achieved cellular, achieved state in the, or desired state in the at time T. We consider here some, I give here some examples here for rule 150, which is linear. We can find a control sequence which is applied to the left boundary cell, and this is the CL, which steers the system in this region, and these cells from 10 to 30, from the initial configuration to a desired, we want only to obtain ones on this area. And this time, of course, all these things are obtained from the relation which gives the T which enter the controllability, the regional controllability in this area. And we have here just some a simulation result when we start with the same initial state. The first, this is of course deterministic CA. The first, which is not controlled, is for this area, and when we apply the control, which is given by the algorithm I showed. As I told you, we want to generalize and to investigate some methods which can be applied to all kinds of cellular automata, even non-linear, even 2D, even no elementary CA. It's a very big challenge, but we are finding, we are given some results. Sorry, I think I have some problem. First, we applied the approach of Markov chain, and we know that the evolution of a control CA, we prove that the evolution of a control CA can be seen as a walk of Markov chain, where the states are the possible configuration, which can be represented in the region omega. We have, if we have two CA configuration restricted to the target region, we can see a relation between these two if there exists a boundary control such that this probability to jump from the configuration S0 to configuration S1, it's equal to 1. In that way, the so-called transition matrix can be constructed in order to describe and analyze a Markov chain. And we obtain a result related to this matrix, constructed from a Markov chain. And for this, we design the graph of the matrix, and we can see if we have two configurations, if there is no link between two configurations, that means that this configuration cannot be reachable starting from the first configuration. And when we study all these graphs related to the matrix, we can go further and look for a time t, time horizon t, for which this matrix could be could give a graph corresponding to a controlled system. The result is very strong because for linear it's proved. The first proof was for linear cellular automata. We prove that this CA will be regional controllable if and only if there is a power t. Then this is the time horizon. This is when we look for a power of the matrix C, of the Markov matrix C, such that all the components are strictly positive. If this happens, the cellular automata is regionally controllable. That it doesn't mean that we obtain how to. It's only to prove controllability. It's not. We prove the existence of a sequence of control that gives the controllability, but this is not the way, because we found other ways, like for the algorithm for pre-images or something like that, to determine the control, effectively the control. But here it's to prove that the cellular automata is controllable. And even we extend this result to nonlinear CA for the case of elementary CA. And here, this is the rule 150, the Wolfram rule. And as I told you, it depends also on the size. And here we have for t equal to 1, it's capital T, sorry. This configuration, the configuration 5 and 15, they have no path between this, there are no link between this configuration, and in that way the matrix, the CA is not controllable for t equal to 1. But here we have all the configuration, there are links between all the configurations, and in this we have this matrix. If we check this matrix, we have all these the coefficients are all positive, strictly positive. Yes, when we worked with the Markov chains, we have also we go to something to another approach, which is based on graph theory, and this approach, the graph theory, it seems to be a good and appropriate tool to study the problem of regional controllability, and we obtained some results on this. According to the existence of an Hamiltonian circuit for the graph, which gives the evolution of cellular automata. Then the CA is, we say that the result we obtain, the CA is regionally controllable if and only if there exists also always this condition according to the time horizon, that the graph associated to the transformation matrix contains Hamiltonian circuits. And this is another result which is related, and we find some bridge between all these approaches. think it's okay for the last sorry. Now I will say about the observability, which is a dual concept of controllability, and the cellular automata is observable by an output operator H if and only if all states S in this state space, they are observable by this output operator. Proving the global observability of a system is equivalent to prove the injectivity of this observability mapping. This observability mapping is to any initial configuration. We map a vector of observations, and this is observation at time 0 to time t minus 1, and we can observe at time t. And then this is not this problem of injectivity of this mapping. It's not related to the observability. It's not related to the reversibility of CA, because when we study the reversibility, it's only to go how to go backward and to reconstruct the predecessors and to study the predecessors if the CA is reversible, but without the application of an output function of observation operator. And this is not the same, because we want to reconstruct and to have the state of the system just according to this observation. Then it's similar. It's some results depending on the size of the cellular automata and something like that. We have this similar hypothesis and similar constraints also for observability, but for reversibility is something different. For the observability is under study now. We have just I just want to say that for as for controllability, the classical criterion and the usual criterion to check and to prove observability of DPs is based off this rank condition. And we just have to construct, to build the observability matrix and say and check the rank condition for this observability matrix, and this is that will prove this is only by this way we prove the observability. We obtain here for CA. And for this is for Affine CA, and what we mean with Affine CA is only linear, but we add one term to here. We give the elementary linear CA and elementary Affine CA, and we can have an Affine CA just +1 or for, and we can obtain a linear CA. I think it's
Samira, I just want to let you know that there's 10 minutes left of the episode.
I think yes. I think it is here. We just I just give some results here without any proof. It's just to give some results for Affine CA and to prove observability of Affine CA by using this rank condition. It depends on, of course, on n, which is the number of the size of the lattice. in this way, the problem is very difficult, because we started just and we can prove and compute only for small size, for cellular automata of small size. For bigger, we have to subdivide the lattice in several sublattices, and observe each one and try to coordinate what we can observe. If we can observe each sublattices, how to coordinate this observation to have some global observation. But this is under consideration now. Then we just for this example, we can have the prove and check the rank of this matrix, and how to reconstruct the initial state by this applying this operator, how to obtain S0 according to the matrix, to the vector Y and gamma, which is dependent on the matrix, the observation matrix C. I think what is the conclusion with for Affine CA? That's what I told you. It's only the beginning. We start to work with the observability and with some specific CA. For observability, we have to check the linearity of the CA, linearity even for Affine, construct the matrix A, eta, and C, and check the Kalman criterion. And if we have, with this, we can obtain gamma and Y, and Y, sorry, and after we can reconstruct the initial state. Of course, there is some advantages. Observability is simple to assess. Initial state can be reconstructed in initial state, but we have some only for Affine, only few C are Affine, because this is only sorry, it's applied for Affine CA. And of course, we are going now to deal with the nonlinear CA, because we are always bearing in mind that the practical applications, and one of the applications we are looking for now, studying, is the fire forest, how to coordinate and to organize the work of the firefighter according to what they observe, and how to coordinate their action in order to avoid the propagation of fire in some vulnerable area. This is what we are doing now, is the extension to nonlinear and to DCA. Also, we are we are studying the graph formalism as well as the sets approach. When we can prove that observability, starting from the initial condition, the initial configuration, we consider the intersection until we go to the final state, what we are observing, and we can reconstruct by using these set approaches. What we are interested in also is the how to choose the structure, the optimal structure of sensors, also the same problem of actuators. But now we are dealing with sensors for this application of fire spread, how to choose the location of sensors, the type of sensors, if they are fixed or mobile sensors. And this is of great interest in order to decrease the computing complexity. This will be what I told you to combine CA with the multi-agent systems and to say how to deal with several mobile sensors in order to achieve in order to achieve observability. Thank you very much, and I'm happy that everything work well. Thank you very much.